Envision that you're standing on the edge of a limitless sea, with a shining universe reflected in its waters. Currently, envision that this scene, with its heap of stars and turning systems, is only a reflection, a projection from an undetectable, far-off shore. This isn't the start of a sci-fi story, but a glance at one of the most striking hypotheses in current physics, the holographic principle. Just as every drop on a cobweb contains the world in miniature, our universe might be an excellent impression of key regulations written on a far-off wilderness, a long way from the strong earth beneath our feet and the vacancy of space. The very texture of our world may be produced by something much deeper, something beyond our present perception. How about we go on this investigation together and attempt to answer the extreme question: does the texture of our universe emerge from a holographic limit? At the core of physics is a journey, a mission to uncover the layers of reality, to reveal its most essential components. These components, known as ontological natives, are the foundation upon which the immense structure of the universe is built. For a long time, physicists have searched for these building blocks, hoping to understand the rules governing their interactions. The journey begins with the concept of space. Isaac Newton, one of the titans of science, imagined space as an absolute, eternal foundation, uninterested in the comings and goings of matter and energy. For Newton, space was a flat, absolute repository, a boundless expanse in which all the events of the universe played out. However, as our understanding grew, this view of space began to evolve. The approach of Einstein's theory of relativity painted a different picture, where space was not just a passive field but an active participant in cosmic interactions. According to the new view, space could bend and stretch in the presence of mass and energy, calling into question the very notion of its supremacy. Amid these shifting perspectives, a revolutionary thought arose: the holographic principle. This principle suggests that our three-dimensional view of the universe might be connected to a multidimensional image, a projection from a two-dimensional surface located at the edge of space. This edge, though infinitely distant and impossible to reach with our current perception, may contain the fundamental data that gives rise to everything we see as reality. This idea challenges our usual thoughts by arguing that the very essence of space, the texture of our universe, may not be an intrinsic trait of the universe, but rather it emerges from something more fundamental. Emergentism describes phenomena that arise from the complex interactions of simpler components, leading to new properties and behaviors that aren't apparent from the parts alone. In the context of our universe, and particularly within the holographic principle, emergentism plays a unique role. The term suggests that the three-dimensional space we travel through and the time we experience are not the fundamental building blocks of reality. Instead, they emerge from a more fundamental or two-dimensional structure, the holographic boundary that encodes the data and laws that result in our perceived reality. In this framework, each star, planet, and system, each law of physics, from gravity to electromagnetism, and the very fabric of the universe, are emergent phenomena. It's as if there is a bridge between the known and the unexplored world, between the observable aspects of our universe and the crucial coding of reality at the holographic boundary. It invites us to rethink not just the design of the universe, but the very nature of reality itself, as we strip back the layers of the universe. Against the backdrop of this theory, black holes, where gravity is so intense that even light can't escape, have become those unexpected legends. Thanks to the pioneering insights of Stephen Hawking and Jacob Bekenstein, Hawking and Bekenstein ventured into an unknown area by attempting to merge the fields of quantum mechanics and general relativity to explore the thermodynamics of black holes. Their theories uncovered the unsettling truth: black holes are not absolute endpoints of entropy, but perhaps central players in the cosmic exchange of information and energy. Entropy, traditionally associated with disorder in a system, took on a new dimension in their grasp. It became a cloak, hiding information within black holes. It was not just about the randomness or disorder of particles, but about the hidden layers of information that characterizes the actual construction of reality as issue twistings into a dark opening. It appears to vanish from our universe, which raises a significant question: what befalls the data it conveys? This question points out entropy as a proportion of confusion, as well as a vital aspect for understanding the destiny of ingested data. The entropy of a dark opening, as proposed by Bekenstein, is straightforwardly corresponding to its surface region, not its volume, an idea that goes against our ordinary comprehension of physical regulations. This connection between surface region and entropy drives us to a significant end. The most extreme sum measure of data that can be contained in any given district of space is resolved not by its volume, as one would instinctively expect, but by its surface region. This view established the groundwork for the holographic principle, which accepts that all the data of a volume could, in theory, be encoded on a two-dimensional surface. Accordingly, Susskind and Bekenstein's revelations of black hole thermodynamics suggest a cosmos in which the actual texture of the real world, each molecule, each force, and the very aspects of existence, must be rising properties, emerging from a deeper two-dimensional texture at the front of spanning the gap between the secrets of black hole thermodynamics and the holographic principle. Juan Meldesena's work is not simply a structure, but the substantial illustration of holographic principles in action. Meldesena's correspondence states a duality between a type of space known as anti-de Sitter space and conformal field theory, CFT, which exists at the boundary of this space. In spite of the positive cosmological constant of our universe, which contrasts with the negative constant of an anti-de Sitter space, the principles derived from this duality provide insight into the nature of gravity and quantum mechanics, and, by extension, the holographic idea of our universe. Key to this dualism is conformal field theory, which works on the boundaries of the universe within the anti-de Sitter CFT structure. CFT is remarkable in its scale and fluctuation. The regulations governing these field theories remain unchanged, no matter what the size or scale at which they are observed. This property of CFT is key, as it encodes the data needed to describe higher dimensional mass space within a lower dimensional system, effectively showing the holographic principle. Scale invariance within CFT is, in addition to being a mathematical nicety, a window into the development of aspects and the actual texture of spacetime itself. Various sizes of patterns at the boundary, represented by the uniform laws of CFT, add to the illusion of three-dimensional space. This peculiarity underlines the holographic principle that the intricacy and aspects of volume space emerge from simpler, scale-invariant elements at the boundary through the prism of anti-de Sitter CFT. Additionally, the complexities of conformal field theory give us a deeper understanding of how the aspects and the actual construction of spacetime can arise. Scale and variation, boundary designs, each contributing to the holographic encoding of the universe. One of the clearest analogies for this complex idea is the concept of nested circles. These nested circles act as visual systems, with each layer representing various scales of boundary designs. The smallest patterns, similar to the tiny level, are densely packed with data and require high-resolution understanding. As you move to larger circles, the patterns become coarser, embodying something similar. Data, however, in a more summed-up, less definite structure, in the tiny space of the holographic limit, the designs are thick and exceptionally detailed, looking like the fine strokes of an expert painter. These fine-grained designs are the most central level of the universe, where each small component is loaded up with data encoding the laws of physics and the introductory circumstances of astronomical phenomena. Moving from the miniature to the full-scale climate looks like taking a gander at a mosaic. Very close, we see just individual tiles, each with its own variety and shape. Be that as it may, a ways off, an intricate and comprehensive picture arises. Correspondingly, the grand design of the universe, stars, and planets rises up out of this aggregate behavior of major patterns encoded on the holographic limit. This change from fine to coarse-grained designs at the limit of the universe isn't simply a component of the holographic model. It's a fundamental process that shapes our impression of space. It underlines the differences in data requirements at various scales, showing the flexibility and efficiency of the holographic encoding of space. The concept of a holographic universe depends on a significant philosophical and logical thought, ontological democracy. This thought proposes that the limits of the universe, with its two-dimensional encoding of data and the three-dimensional space we know all about, can be equally basic to the texture of reality. Nor is one more genuine or essential than the other. Rather, they coincide in a condition of common development. This view has sweeping implications. It suggests that what we see as the three-dimensional reality of stars, worlds, and planets, all with their complicated connections, may be the sign of deeper, more crucial regulations encoded at a far-off, further, and visible limit. Now, this coding not only directs the construction of the volume but also is shaped by events within it, making a feedback loop. In our journey through the holographic universe, we experience a significant rethinking of gravity, which is traditionally seen as the bend of space-time under the action of mass. In the holographic system, gravity emerges not from the mass itself but from entropic forces acting in the data encoded at the limit of the universe. Now, the idea that gravity may be a new phenomenon, like temperature or strain in thermodynamics, represents a radical shift in context. It suggests that what we see as gravitational attraction is the consequence of the universe's inclination to expand entropy, a thought initially proposed by physicist Eric Berlin. This hypothesis proposes that gravitational attraction arises from changes in how much data is related to the position of material bodies. The holographic universe, moreover, pushes us to explore the mysterious role of quantum entanglement in the fabric of spacetime. Quantum entanglement, the phenomenon in which particles remain bound so that the condition of one molecule can momentarily influence the condition of another, no matter what the distance separating them might be, is the string that winds around this spatial continuum of the universe. According to this view, space itself emerges from the entanglement of quantum bits encoded at the vast limit. When particles are entangled, they share a common bond that contributes to the illusion of continuous space. Theoretically, unwinding these particles could lead to the vanishing of the space between them, which raises questions about the very concept of distance and region in our universe. The standard of a holographic universe, obviously, like many other speculations in physics, presents one extreme question, the topic of finding a general holographic model. This ambitious undertaking is designed to reconcile the complex intricacies of the universe into a single structure that precisely describes both the grand scope and the details of quantum mechanics. The challenges in this attempt are huge. Creating a universal model requires not just a deep understanding of quantum mechanics and the general theory of relativity, but also a new approach to integrating these theories into a holographic system. Potential breakthroughs vow to reform our understanding of the universe. An effective, all-encompassing holographic model could provide extraordinary insight into the origin of the universe, the nature of black holes, and the fundamental regulations governing reality. As we venture through the possible outcomes of the constraints of this hypothesis, we might be on the brink of a new understanding of the universe or another invalidation of a prominent theory. If the truth is holographic, our insight, experience, and very existence might be far more entwined with the universe than we ever imagined. This journey is filled with challenges and questions, but the promise of unlocking the deepest mysteries of the universe drives us forward in search of a groundbreaking universal model that would rethink our position in the universe.